Hello everyone, welcome to the lecture. Myself Devananda Rao, working as Associate Professor in the Department of CSC, MLR Institute of Technology, Hyderabad. Today's topic is Finite State Automata. Finite Automata. A language is a subset of the set of strings over an alphabet. A language can be recognized by a machine. Such a device is called a recognition device. A language can have a representation in terms of generating device as grammar as well as in terms of recognition device, which is called an acceptor. So, the language can be represented in two ways. That is, as a generating device is called grammar. Grammar can generate a language, as well as the language can be represented in terms of device that is called recognition device is called an acceptor. That is, language can be accepted by the machine. The simplest machine or recognition device is the finite state machine or finite state automata. Example of finite automata. Let us consider a man watching a TV in his room. The TV is on state. When it is switched off, the TV goes to off state. When it is switched on, it again goes to on state. This can be represented by a state diagram. See, initially the TV is on state. Two states are there, TV on state, TV off state. This is initial state. When TV is switched off, the transition occurs. That is, the transition occurs, control goes to TV off state. The state of the TV changes to off state. When it is switched on again, it goes to on state. So, this is a best example, simple example for finite automata. So, the action is switch off. This is switch on. When TV is on state, when you switch off, the TV will goes to TV off state. When the TV is off state, when you switch on, the control goes to TV on state. The TV changes its state. This is the best example to understand the finite automata. Next, finite automata are used to recognize patterns. It takes the string of symbols as input and changes its state accordingly. When the desired symbol is found, the transition occurs. At the time of transition, the automaton can either move to next state or stay in the same state. Finite automata have two states, accept state or reject state. When the input string is processed successfully and the automaton reaches its final state, then it will accept. So, after the input is processed, if the automaton reaches its final state, then we can say that the string is accepted. The automata having initial state as well as final state. The formal definition of the finite automata. A finite automata is a 5 tuple, that is Q sigma delta Q naught F, where Q is a finite set of states, sigma is finite set of input symbols, Q naught is the initial state, F is the set of final state, delta is the transition function. Delta is the transition function. 5 tuples. Finite automata model. Finite automata can be represented by input tape and finite control. This is the input tape, this is the finite control. Input tape is a linear tape having some number of cells. That is, the tape is divided into number of cells. Each input symbol is placed in each cell. That means, each cell will contain one input symbol. So, the tape is used to store the input. Finite control. The finite control decides the next state on receiving particular input from the input tape. The tape reader reads the cells one by one from left to right, and at a time only one input symbol is read. So, the tape read head can read the symbol from the tape. At a time only one symbol we can read. So, that based on the input symbol and current state, the finite control will take the decision whether to move to next state in the machine or stay in the same state. So, this diagram is showing finite automata model. Then types of automata. There are two types of automata, that is deterministic finite automata and non-deterministic finite automata. DFA, that is deterministic finite automata. Deterministic finite automata refers to deterministic finite automata. Deterministic refers to the uniqueness of the computation. In the DFA, the machine goes to one state only for a particular input character. DFA does not accept null moves. Here, DFA computation is unique. That means, for a particular input symbol, the transition uniquely identified. That means for one input symbol only one transition, that is only going to only next state is only uniquely identified, next state is uniquely identified, and also epsilon moves will not be allowed in DFA. Coming to NFA, NFA stands for non-deterministic finite automata. It is used to transmit any number of states for a particular input. That means in NFA, unlike DFA, for a particular input we can define more than one transitions for a particular input. That means more than one states, outgoing states will be identified for a particular input symbol. And also NFA can accept null moves. Epsilons are accepted in this NFA. That is the main difference between NFA and DFA. Some important points about DFA and NFA. Every DFA is NFA but not NFA, but not vice versa. That means every DFA is NFA but NFA is not DFA. There can be multiple finite states in both NFA and DFA. DFA is used in lexical analysis phase of the compiler. NFA is more of a theoretical concept. Next, deterministic finite automata. The formal definition of the deterministic finite automata. It is a 5 tuple Q sigma delta Q naught F. Q sigma Q naught F and delta. Q is set of states, total number of states in the finite automata. Q represents set of states. Sigma represents set of input symbols which machine takes as input. And Q naught, initially we will use initial state as Q naught. Q naught is the initial state or starting state of the machine. F is set of final states. Delta is a transition function defined as Q cross sigma to Q. Delta is a transition function Q cross sigma to Q. That means Q is a state, sigma is giving input symbol. For a particular input from the state we can define next state, that is transition from one state to other state. In a DFA, for a particular input character the machine goes to only one state, that is uniquely next state will be identified. A transition function is defined on every state for every input symbol. This is very important point. In DFA, for every state and for every input symbol we have to define the transition function, that is delta function we have to apply for every state in the machine and also every input symbol. Also in DFA, null moves or epsilon moves are not allowed. That is DFA cannot change state without any input character. If there is no input, no transition. For example, construct DFA which accepts language of strings, all strings ending with A. The input alphabet is sigma is AB. See, here the input alphabet is AB, A comma B. By using these symbols A and B, we can construct strings, combination of A's and B's. Strings contains A's and B's, but the string should end with A. The last symbol must be A. Before that, we can have any combination of A's and B's. A is a valid string, B is a valid string, B A is a valid string, all A's followed by B followed by is a valid string, A B is a not valid because last symbol is B. So, for all strings ending with A should be accepted or recognized by the DFA. We are asked to construct the DFA to accept such strings. Here, the language containing set of strings, all strings are ending with A. Here the string only one symbol. Here AA, last symbol is A, AAA, last symbol is A, 4As, last symbol is A, 5As, last symbol is A, BA, A is a last symbol, like that. Then above is simple subset of possible acceptable strings that can many other strings which ends with A and contains symbols A and B. So many other strings also having last symbol A, but these are the sum of those strings containing last symbol A. For that we need to construct DFA. So we need to take initial state, Q naught is the initial state. So if you read input, we have input alphabet A, B, either A or B. For every state like Q naught, we need to define delta function for A and delta function for B. So one state is there, initial state, there is initial state q naught. For q naught and A we need to define the transition. For q naught and B we need to define the transition. So, in q naught if you read input as B from the input tape, stay in the same state, because the q naught is if you read A, that may be last symbol, last end of the string, so that I can go to final state q1. As long as if you read B's, stay in the q naught initial state, we cannot move to next state, because B is the string should not end with B, so that those strings ends with B will stay in the non-final state. Those string end with A, for those strings the machine will stay in final state. Okay. Then for q naught on A, the machine will go to same state q naught. For q naught on B, q naught on A going to q1, q naught on B going to same state, q naught on B stay in the same state, q naught on A going to q1. So, for q1 also we need to define transitions for all inputs q1 on B. So, q1 is a final state, already we have seen A. If next symbol is also A, that may be last symbol of the string. So, that for A in q naught stay in the same state, from q1 for A stay in the same state. In q1 if you read B, go to non-final state, q1 on A stay in the in q1 if you read A, stay in the same state, in q1 if you read B, going to q naught. This is the transition diagram for the language consisting combination of string symbols A and B, but end with A. Next, transition table. This is q naught is the initial state, q1 is the final state. Final states are represented with the star. Then q naught on A going to q1, q naught on A going to q1, q naught on B going to q naught only, q1 on A going to q1, q1 on B going to q naught. So, this is transition table, state transition table, this is state diagram. And strings not accepted are any string end with B are not accepted, these are invalid strings. Then non-deterministic finite automata, NFA is similar to DFA except following additional features. Null non-deterministic finite automata, NFA is similar to DFA except following additional features. Null move is allowed, that is epsilon is allowed in NFA, it can move forward without reading any input symbol. So, without any input symbol, NFA will move to next state. Ability to transmit any number of states for a particular input. So, unlike in DFA, NFA can move to more than one next state for a particular input symbol. However, these above features do not add any power to NFA. So, in terms of power, NFA and DFA both are same. If you compare both in terms of power, both are equivalent. Due to the above additional features, NFA has a different transition function, the rest is the same as DFA. See, delta is a transition function Q cross sigma union epsilon, because epsilon is allowed in NFA going to 2 power Q. This is a transition function of NFA, NFA transition function. This is DFA transition function, DFA transition function is Q cross sigma to Q only. So, Q is contained in 2 power Q. Q is contained, right, that is RHS of these transitions functions, Q is contained in 2 power Q. So, that DFA, every DFA is also NFA, but not vice versa. Then, as you can see in the transition function is for any input including epsilon, NFA can go to any state, number of states. For example, below is NFA for the above same problem, that is strings end with A. Initial state Q naught is initial state for any input symbol A or B in the, for example, see, if for input symbol A, you can go to Q0, from Q0 to Q0, or I can go to Q1 final state. In Q0 for input symbol B, you can stay in the Q0 also. Also in Q1, unlike in DFA, there is no need to define transition functions for all the symbols and all the transition states. In DFA, you need to define the transition function for every state and symbol. So this is the NFA for the same problem, like that transition table. Q0 on A going to Q0 as well as Q1. So that Q0 on A going to Q0, Q1. Q0 on B going to Q0. Q1 there is no transition, that is why pi. Q1 on B there is no transition, that is why pi. Since all the tuples in DFA and NFA are the same except one of the tuples, which is transition function delta. In case DFA, this is the transition function Q cross sigma to Q. In NFA, transition function is Q cross sigma to 2 power Q. 2 power Q. Now if you observe, you will find Q cross sigma to Q is part of Q cross sigma to 2 power Q. So that if you observe RHS, Q is subset of 2 power Q, which indicates Q is contained in 2 power Q. Q is part of 2 power Q, and reverse is not true. So mathematically we can conclude that every DFA is NFA but not vice versa. Yet there is a way to convert NFA to DFA. So there exists an equivalent to DFA for every NFA, so that we can convert any NFA into its equivalent to DFA. Thank you.